have a problem session starting at 10:15 in my meeting. Continue and then I'll be afterwards after we discuss. Right. So last time we were discussing. Let's see. Hold on 1 second. Right, so we were discussing some of the really foundational understanding of wave mechanics. How we think about the wave function. So, fundamentally, the main interpretation of the wave function, of course, is the wave function related to probability amplitudes. And the square of the wave function at a particular point telling us about the probability density to find the particle at a particular point in space, or in as a density, obviously, at some given time. And that probability density in a mechanical system will generally flow. And that flow equation, that kind of equivalent of fluid flow that we think about, is described by the continuity equation. So the continuity equation is familiar mostly to most of you, I'm sure, in the context of electricity and magnetism, where rho is the charge density and J is the current density of charge, but it's a general statement of flow of fluid, whatever that fluid might be. And the physical meaning of the continuity equation, of course, is conservation of whatever stuff is flowing. In this case, it's thought about as the conservation of probability, which really is to say that what we're saying in this situation is that in a system where we're described by a potential, where the potential is a real function, the particle is neither created nor destroyed, it just moves. And that movement is described by the flow of the probability density, and that is described by the probability current, which, written in this form, we see as whatever the local density is times a sort of effective velocity of flow, and that effective velocity of flow is determined by the gradient of the local wavefront to the system. So we think about the probability flowing along rays, which are the normals to the wavefronts. Okay? All right. So, moreover, of course, one of the foundational ideas which laid at the heart of the whole development of the quantum theory was the understanding of wave-particle duality. I mean, wave-particle duality is where the whole idea of the probability amplitude arose, and all of the craziness that we've been talking about relative to quantum mechanics came from trying to understand the nature of the world and the foundations of physics. Newton come from really two things: mechanics and optics. And trying to understand the nature of the motion of the heavenly bodies and the nature of light is really the foundation of physics. And there were sort of course, within that, particularly in optics, there were the competing theories of optics, the particle theory, the corpuscular theory, as Newton called it, and the wave theory, which was Huygens' idea of what the nature of light was. Okay? And so in the sort of particle picture, we have the idea of a ray of light that moves along a particular trajectory. Okay, that was, Newton thought as reasonable that light was made up of tiny little particles that were streaming at super high speeds and there were forces exhibited or exerted upon them by material, which caused them to refract, and reflect. In modern theory, we know that the ray theory of light is a limit of the wave theory of light in the short wavelength approximation. And the description of rays is unified with the description of the motion of particles and the mechanics of Lagrange and Hamilton. So I've it's not a very nicely written chart, I'm trying to write this out in my notes more clearly, of the complete analogies between these things. So in the ray theory, the equation of motion of the rays follows from an action principle. That is stationary, the trajectories of the rays are the stationary functions, the solutions which make the action stationary under perturbations around those trajectories. And that's codified in Fermat's principle. Fermat said in the 17th century that we can understand the trajectory of a light ray in a medium in terms of minimizing the time it took for the light to get from one point to another. But in modern parlance, what that's saying is that there's an optical path length, and we're minimizing the optical path length. And the optical path length is determined by the local index of refraction. Sorry, switch from part of it. And the solution to this is basically the Euler-Lagrange equation that we know from this side, where the motion of the particle in a potential is determined by the stationary action, and the trajectories which minimize the action, where the action is unchanged with small perturbations around those trajectories, are the Euler-Lagrange equation, which is Newton's law, F equals ma. Right? Okay. So that's the particle picture. Competing with that is the wave picture. In the wave picture, we have a wave equation. The equation of the wave, say for the electric field, moving, which has some frequency omega, moving in this index of refraction, this index of refraction is this. And the Huygens principle basically says that the rays are the normals to those wavefronts. And if we have the iconal approximation, which is to say when the wavelength is small compared to whatever the length scale for change of the, say, the index, then we have a solution which is the same as this. Okay. And the iconal approximation, so under the iconal approximation, the we have a wave, this is the wave solution, whose rays follow Fermat's principle. Okay, this is an approximation. Under that case. Now, on this side of the equation, there's kind of an interesting history. So, this equation, which I have no room in my horrible planning, this is the Hamilton-Jacobi equation. The Hamilton-Jacobi equation follows from classical mechanics. It's not a wave theory. It's a mechanical theory. But what we have seen is that this equation follows as the geometrical optical approximation to the Schrödinger equation. In which case we understand that classical dynamics of a particle, the trajectory that a particle follows in the classical limit is the limit where the wavelength of the de Broglie wavelength of the particle is sufficiently small compared to the length scales over which the forces change, which would cause diffraction of those waves. And when we don't have such diffraction, then we have rays, and those rays follow the classical trajectories. That also gives us a way of writing down a solution to the Schrödinger equation when we're in this approximation. And that is known as the WKB approximation, where we basically use the Huygens wavefront associated with the surfaces such that the rays of those wavefronts are the classical trajectories. So when the wavelength, the de Broglie wavelength of the particle is sufficiently short compared to the length scales over which the potential is changing, we can write down an approximate solution immediately. In fact, the amplitude here is related to 1 over that. We wrote down that solution last time. Okay? So of course, all of these things are unified together. There's one, in some sense, what we see is these two equations are the same. And the unification of them is wave-particle duality. So, in wave-particle duality, particles with certain energy have certain frequencies, and particles with certain momenta have certain wave numbers or wavelengths. Right? Obviously from freshman physics. And what we see here is that the unification between the wave and the particle theory is to say that we can have our general action principle here, which is, again, always minimizing this optical path length, but these are in fact the same thing. That this action from the point of view of Hamilton, this is the same thing as the Lagrangian here, inside here. Right? This is the Lagrangian dt, which is this. And for a constant energy, this was P dx minus E times the time difference. And with this relationship here, this is equal to k as a function of x dx. that's what times h bar. Minus. So it's the same, this action principle is the same as this action principle, because what is k? K as a function of x is omega over c times n of x. In optics. Or, what we have over here, it's the momentum as a function of x over h bar, which is equal in mechanics to the square root of twice the total energy minus the potential energy. Right? That's what's going in here. So we have exactly the same unified theory. There are waves. There are rays, which are limits with short wavelengths, and they have this exactly the same action principle where the effective index of refraction in mechanics is given here. Okay. So notice that though that there is this kind of weird relationship, a bigger potential here corresponds to a smaller index here. Notice in particular, if I look at the phase velocity, of a wave, right, that's omega over k. If I look at what that is locally at some position of space in this ray picture, of course, if I write in the wave-particle duality, this is this. Which is a curious thing. What it's saying is that the velocity of these wave fronts that move in order to ensure that the normals to those wave fronts are the classical trajectories move inversely with the speed of the classical particle. Which is why Newton got it wrong. Newton said that inside a material, light moves faster. The only way he could get refraction to work. Now, no one could measure the speed of light at Newton's time. So maybe Newton was right. But Huygens' principle kind of took over, and once they measured the speed of light and they saw in fact the speed of light moved slower, then that doomed the particle theory. The particle theory of light was thrown out. It was totally bogus theory.
Well, it was hard for them to measure between C and half C.
Because they couldn't measure anything fast at that time. So that's an interesting fact. However, it is quite curious that Hamilton-Jacobi equation is, and Hamilton knew this, that he could understand the trajectories of classical particles as the rays of a wave fronts. We didn't call them wave fronts, but these surfaces that were moving. But interestingly, well, not interestingly, there's no way that he could have guessed that in fact the classical mechanics was the ray optics limit of a more fundamental wave theory. But it is, and it's all together. Now, this unification is pretty clear. There's, of course, many subtleties to this. Should we think about the electric field as the wave function of the photon? Kind of. The subtlety, the problem is that the photon is a relativistic particle. It's as relativistic as they get. And relativistic quantum mechanics has some differences with respect to the non-relativistic mechanics. The notion of localizing particles, you can't do that because particle number isn't conserved. And what it means to measure the position of a particle relativistically is a much more subtle question. As I said, position is demoted. It's no longer an observable in quantum field theory. But nonetheless, these analogies should be kept. Final thing, of course, we talked about a little bit at the end of lecture last time, the idea of the path integral. And I would encourage you to read about that some yourself. There's a nice sort of beginning description of it in Sakurai's text. And Sakurai's text is quite good. I recommend trying to get a hold of it if you don't have it. We can understand the quantum mechanics in saying that instead of having a single possible trajectory quantumly, in some sense, the system explores all possible trajectories, and they're weighted by a probability amplitude that's given by the local action of that trajectory. And that principle that connects classical dynamics and classical action of quantum dynamics is a foundation of quantum mechanics. And we use it all the time, particularly in quantum field theory and in statistical physics as well. So I would encourage you to take a peek at that. Okie dokie. All right, so now let's get into some nitty-gritty. So given this, we're just going to go at lightning speed today, talking about wave mechanics in one day. Something you've studied over and over again, parts on the box, all that stuff. I just want to get some of this, some of the foundations down. So we have some potential as a function of x. Right? Let's say it looks like this. And what we call the zero potential energy is irrelevant. And I kind of want to check that a bit above because it just ruined my patience. So, classically, of course, we have different kinds of motion that can exist in such a potential, right? Remember, of course, we have a potential, energy is conserved. So specifying the energy and the initial condition completely specifies the trajectory, classically, right? That's, the standard tricks you do. You want to throw up a ball, how high will it go? You could just use conservation of energy to do it. So, for example, if a particle started at some position, if its energy was this and it started at some position, it will oscillate between these 2 points, or turning points. Because, of course, the kinetic energy must always be bigger, it has to always be bigger than or equal to the potential for all x. It's a positive number. Alrighty, so this is one kind of solution. If we started up here, then I'll have this one turning point, right? So this is another possible trajectory. I can come in here, bounce off, and come back. If I started over here at this energy, I'll hit this guy and bounce back. If I started over here at the same energy, then, of course, I'll hit this turning point and bounce back.
Can the tunnel through the...
This is classical. So now let's, of course, talk about the quantum mechanics. So classically, we have this supposed to be at the same energy. So this, of course, in this case, this kind of solution we call scattering. So a particle will scatter off this potential. This is also scattering. This is bound motion. There's the bounce motion of the particle. Okay. Now, of course, you know, and as Stephen alluded to, if I look at this, so I look at my Schrodinger equation in 1D. This is the equation that we just, the time-independent Schrodinger equation has this form. Where K is the momentum, local momentum over HR, which is 2m e minus v of x. Right? So, as we said here, classically, k squared can be negative. Right? Classically, p is a real number, which means that it must always be the case that p squared is positive. Right? So that's said over here. So, with that, but of course, quantumly, k squared can be negative. There's nothing that forbids that. Which means that k of x for when the e less than b of x, this is an imaginary number. So that means the local solution, if I think WKB like.
Could that be k squared equal to I k kappa squared?
No, k squared is minus kappa. Because k squared can be negative. So the WKB solution, which gives us a hint of things, will be of the form e to the minus kappa with these kinds of exponential tails. Of course, what that means is that what was classically forbidden, this region, the particle, if it had this energy, it cannot be in this region because it's not classically forbidden. Now it's classically allowed. It means, of course, we can tunnel. And so we have tunneling classically. I mean quantumly. Moreover, these two solutions now can be, in some sense, become mixed. So what that means is that when I have this kind of situation, I can have I can have a scattering resonance, as we will study next semester. If you come in with a certain energy, which is resonant with a quasi-bound state, then there is a particular kind of scattering that occurs due to the fact that the particle can tunnel in and rattle around at a resonant energy and then tunnel back out. It gives a much stronger kind of scattering interaction. We will see. Moreover, if I started the system here, classically, whereas it would be bound, quantumly, it has a finite lifetime, and it's only quasi-bound, and it can ultimately tunnel out. And that means, in some sense, that the particle inside this potential has a finite lifetime. All right? All right, so what can we say? Some general properties of the solution. So firstly, if we look at this kind of potential, if is non-singular, doesn't blow up anywhere, okay? Now you're first studying probably your homework at the delta function potential, so this won't quite apply. If the potential is non-singular, we say a few things just from the solution to this kind of equation. By the way, this kind of differential equation fits under a certain, 19th century study of ODEs. It's known as Stern-Liouville theory. And it's been well studied back then. Maybe, I don't know, you guys talk about it in 466? I don't know. Probably not. Anyway, what can we say? Firstly, the solution is continuous. Okay? So that's one thing we can say. Its derivative is everywhere defined. Moreover, the solutions we seek in the solutions of that's our Hilbert space that we've talked about, the square normalizable functions on the line. Okay. Now, what that means is that for bound states, because we have to satisfy the boundary conditions, and because we don't want the solutions to blow up, because we want to be able to look for normalizable solutions in here, then we have discrete solutions, discrete possible energy eigenvalues. Okay. The unbound states are trickier. Generally, the unbound states Well, as we know, if we have a free particle, the energy eigenstates we can write down are plane waves. Plane waves are not normalizable. They are not in this set of square normalizable functions. Nonetheless, they form a basis of possible functions for this. And so we care about them for that reason, because we can always write a wave packet or a superposition of the unbound states, which is a physical state. Okay? But that means because we don't have this kind of boundary conditions to worry about here, then all we don't want is, so the unbound states is, they should be normalizable like a delta function. So in other words, they don't blow up more than a delta function. The unbound states, though, don't have these boundary conditions, so we have a continuum. Of possible energy eigenvalues. So what that means is that the solutions to the energy eigenvalue problem which is in the position representation is this equation is this equation written in the position representation, right? Then the solution to that form a basis, which means we can write a resolution of the identity in terms of generally the n-bound states and then in addition the scattering states. So we have to integrate over all bound unbound energies. That's the resolution of the identity. Note, when we talk about the scattering states, typically, because of the way we integrate over them, we typically give them units, right? They can't have to have the units of 1 over the square root of n. Just like when we had the kets in x, they have the units of 1 over the square root of length or volume. Okay. This is often forgotten, that this has to be in the resolution equation, but it does. Now, it might be that the support of your wave function is dominated, has support mostly on these vectors and not on the scattering states. But if you really want to be formal and be careful, you have to think about both the bound and unbound contribution to your resolution of the identity. All right. Now, one thing we can say about the solution, another thing we can say about the solutions is about degeneracy. Well, for the unbound states, the scattering states, we have uncountably infinite degeneracy. We already saw that in the case of the free particle. right? The free particle, the energy is p squared over 2m, kinetic energy. But any plane wave moving with that momentum, but in a different direction, is also an ion state. Okay? What about the bound states? Well, the answer to that, as we will show in a moment, and you probably have seen before, the bound states means there cannot be degeneracy. No degeneracy in 1D. This is all about 1D. Of course, you know about higher dimensions, like the hydrogen and so forth. We'll get to that in a little while. How do we see that? Get here. For us, see. Let's see. For you give me in the same way as classically, you give me the energy, and that determines the trajectory. In quantum mechanics, you give me the energy, and that determines the wave function, the bound state wave function. That's not true in higher dimensions, right? If I tell you the energy of a planet moving around the sun, the energy alone is not enough to tell me the trajectory. I also need to know the momentum, right? And the projection of that momentum as well. If I have those three, then I can do the Kepler orbit. And the same thing is true quantum number. Those are the three quantum numbers. The principal quantum number, the L quantum number, the M. All right, how do we prove this? We have to remember how to do it because it's not really here. So, let's say, consider two solutions. At the same energy. So, I have two solutions, psi 1 got the same K, and psi 2, or U1 and U2 doesn't matter. So let's multiply the first equation by psi 2 star, and this equation by psi 1 star. Let's subtract. Actually, I don't think I want to multiply by the star. I just want to multiply by that. Okay, so that means that d by dx of psi 2 d psi 1 dx minus psi 1 d psi 2 dx is 0. Which means that this, which is the Wronskian, is a constant. As a function of x. Okay? So what that means then is that the derivative of psi 1 dx over psi 1 is equal to d by d psi 2. Which means if you just integrate that, that psi 1 of x is proportional to psi 2 of x. If you integrate that, you get the log, it's equal to the log, and that means that 1 is just the constant of times the other. And because you can always renormalize it, it means, I skipped an important point because this doesn't follow. What is this constant? Because this says the constant is 0. S is equal to this. Otherwise, it's constant. For a bound state, it must be the case that at infinity, so if the domain extends to x goes to plus or minus infinity, the wave function has to go to 0 for a bound state, right? Because otherwise it would be either the plus x and it would blow up, and that's not an allowed solution. So if that's the case, this goes to infinity, then the size goes to 0, which means the constant is 0. And then it follows this. So that's why it's important as we talk about bound states. Otherwise, it just doesn't follow. So that means because they're proportional, normalization says that psi 1 must equal psi 2. So it's the same solution. So if we have the energy, we have the unique, there is a unique wave function for a bound state corresponding to that. That's the same thing that's true classically. Classically, you give me the energy. If it's a bound state, there's one trajectory. All right. What else can we say general things about? So for bound states, from Sturm-Liouville theory, first of all, you can prove the following thing. The lowest energy solution has no nodes. And so, of course, what we call the ground state. Moreover, each subsequent higher energy state has one more node. Now, why does it kind of make sense physically that excited states and more excited states, states that have higher and higher energy, have more and more nodes? Why would that? Forgetting about Sturm-Liouville theory, which is where this stuff follows, you can prove this mathematically. Why would we expect that? Do we have any in here somewhere, anywhere? Oh, there. Oh, that's not good. This is maybe okay. All right, so. So let's look at, suppose I have, why would we expect this wave function to be a higher energy state than this wave function? Well, I mean, what we know is something about the relationship between kinetic energy and the derivative of the wave function, right? So the kinetic energy let's say about the average kinetic energy that. So states which have bigger changes in their curvature have higher kinetic energy. So you kind of expect that. If you're going to keep curving the wave function more and more, a wave function with lots of curvature has higher kinetic energy. So curvature all right. So what next? Well, there's one important class of problems that we often solve, and that is the reflection symmetric potential. That is to say, if the potential has reflection symmetry, whatever that is, then there is important properties that follow to the solutions to the Schrödinger equation. And that means the following. So the reflection symmetry is known as parity. Parity is we've talked about briefly the idea of continuous symmetries like space translations and rotations. Parity, which is reflection through the origin, so in 3D, that means x goes to minus x. So if I draw this, here's my position vector x, and I reflect it through the origin. Turn minus x to minus x minus y to minus y, z to minus z. Okay? So that's reflection through the origin. In 1D, that's just along the x-axis going from x to minus x. Okay? So the parity operator is a unitary operator because we know that all symmetry operations are what's the word I'm looking for? They're they can be performed by unitary transformations. So the parity operator, I'll call P, or pi in Greek, does the following. It also turns the momentum operator minus the momentum operator. And we see clearly from this that this is unitary. Because if I do it twice, in the inverse of it, What are the eigenvalues of parity? Well, it's a unitary operator. But we see here, under this definition, the parity operator is actually, its adjoint is actually equal to itself. Because the inverse operation is, again, the same operation. So this says that when you do it twice, you get the origin. I mean, you get the identity. So what are the eigenvalues of this operator? Plus or minus 1. We know they have to be unit magnitude complex numbers. They're e to the I0 and e to the I pi. Because every unitary operator, its eigenvalues are phases. All right. So, how does the parity operator act on an eigenket? Well, it turns the eigenket to the position eigenket at minus x. Right? And so, if I look at the wave function, so I have a state psi, and its wave function is, of course, the position representation of the state. What is the position representation of the parity operator acting on psi? Well, if I look at the position representation of that vector, it's that. And this is the equivalent of the dagger of pi dagger acting on that. But this is equal to its own adjoint. So that is equal to minus x. So that's this evaluated length. So the parity operator flips the state to what its value is on the at minus x. All right, so what can we say about this? Well, let's suppose we have a potential which is reflection symmetric. Well, written as an operator, so my Hamiltonian is 1D, p squared over 2m plus v of x. If the potential is reflection symmetric, what it says is that if I do the unitary transformation on this potential operator, that evaluates this as this, right? And if this is reflection symmetric, this is this. The kinetic energy is reflection symmetric because p goes to minus p, but this is p squared. Which means that the Hamiltonian, if the potential is reflection symmetric, the kinetic energy is always reflection symmetric. Therefore, the Hamiltonian is invariant under parity. That is to say, if I do this transformation, I get the Hamiltonian back. And what that means is that if I multiply by pi on the left, yeah. Or equivalently, H commutes with parity. So this is an important result. For reflection symmetric potentials, the Hamiltonian commutes with the parity operator. Okay. Now, if two operators commute, what can we say about their eigenvectors? That at least they can be the same. There exists a common set of eigenvectors of both the Hamiltonian and the parity operator. Okay. But so this refers this as there exists common eigenstates of parity and Hamiltonian. However, we can say more because the only way they could be different is if there's degeneracy, right? Because when we can have degeneracies in the eigenvalues, then there can be different eigenfunctions that we can take superpositions of, which might be eigenvectors of one operator, but not the other, as we discussed with those block diagonal matrices and all that at the beginning of the semester. However, if we're talking about bound states, that extend to infinity, then we say there's no degeneracies. Which means for these cases, energy eigenstates are eigenstates of parity. So that means that if I have a solution that is the nth bound state, that this solution is an eigenstate of parity, which means that this has to be plus or minus that. Which means in wave function language, if I multiply the ket here, that un of minus x, right, that's x on that, is plus or minus that. Which means that the solutions, the bound state solutions in 1D are, for a reflection symmetric potential, are either symmetric or antisymmetric.
So basically it's an odd or even function?
Correct. That's what I mean. Even or odd. So let's look at some simple solutions. Of course, the solution we all know off the top of our head is the particle in a box. So, before I do that, I guess I should say the following thing, of course. The solutions that are easy to write down, or not easy, but quickly we can write down, are solutions with piecewise constant potential. What I mean by that is that my potential is a constant, V1, V2, V3, V4, etc. Okay, so we can write down those solutions instantly because in that case, I'll just call it V0. In any region of space where the potential is constant, then my Schrodinger equation takes the form of effectively the simple harmonic oscillator, ODE. Where K0 is the square root of 2n e minus v0 over h bar squared. Okay. So we have two kinds of solutions in the classically allowed regions. K0 is real. In the classically forbidden regions, K0 is imaginary. In this region, the solutions are of the form either the plus or minus I K0 x, or sine and cosine. And in this region, the solutions are either the plus or minus kappa x, or cosh and sinh. So depending upon the energy, here in this region it's classically forbidden, here it's classically allowed. All these regions are classically forbidden, this region is classically allowed, this region is classically forbidden. And so what you do, and you've done this, is you put these solutions in and you match them at the boundary conditions with the condition that the wave function doesn't blow up. So here the wave function has to grow like e to the plus kappa 1x. And here it goes like e to the minus kappa, I'll try to call this 8. And then inside here I have the sines and cosines, and you have to match that the wave function is continuous and the wave function is derivative is continuous, because of what we say over there, this and this. in here, even though the potential is not continuous, the wave function is. Now, say a couple. If V naught goes to infinity, then kappa goes to infinity, which means the wave function does not tunnel into the spin region. So if I have a potential that's a square well, and this goes up to infinity, then we know that the solutions can't penetrate in. In fact, you can sketch solutions. They have to be eigenstates of parity. So they're cosine, sine, cosine, 1, 2, 1, 2, 30. Yeah, yippee. Something's wrong.
These 4 peaks.
This guy goes in the middle. Yeah, looks like that. Etc. Up the line. So we have cosine. Etc. Sine. Up the line. Okay. In this case, we can write down the solutions automatically because the solutions are eigenstates of parity. And they must alternate because the eigenstates of the Hamiltonian are also eigenstates of parity. And because every wave function has one more node, we go from an even to an odd, to an even to an odd. Okay. If this was a finite potential, again, the same thing would be true. So if I had a potential where this is now V naught, and V naught is not infinity, well, now I can penetrate in a little bit, and I have solutions like that. And there's a finite number of downstates. Again, we can alternate them from even parity, odd parity, even parity. And know from the fact that they must go from even to odd to even, how this guy must be at e to the plus kappa x, and over here e to the minus kappa x for the even guy. Whereas on the other side over here, we have the other kind of solution. This is e to the kappa x, and this is minus e to the kappa. Okay, because it has to be odd. So you should use parity when you have it. Now I want to conclude with one last thing about this. And again, I'm not going to go through these details. They're in the notes. You've solved these problems before many times. Part of the box, this kind of one-way mechanics. We're not going to do it here. You have some homework to review those things. But I'm not going to go through that in detail. But I do want to say one last thing in our obligatory 5 minutes open course for the last thing. Suppose that I have a double well. Well, it's not, doesn't look so perfect, but it's supposed to be reflection symmetric. Okay. Reflection symmetric about this guy, right? So we know in this situation that the eigenstates are the eigenstates of parity. Okay? And they alternate from even to odd to even to odd. And the ground state has no nodes. So we could sketch that. The ground state solution, if it was a particle in a box, it tunnels in. That's the ground state.
Can I sit just a little bit?
What's that?
Can I sit and listen?
Yeah, we're going to quit in 2 minutes, but you
That's
can.
what I was-
That's it. The first excited state has one node, right? And where is that node? It has to be in the middle because it's antisymmetric. So the first excited state with some energy over here looks quite similar. It looks like that. The next excited state will be at a much higher energy. Of course, it's got to be an even parity solution. And then the next one is an odd parity solution, which looks quite similar, but has the opposite parity. So these solutions come in pairs of symmetric and antisymmetric combinations of the particle localized in one or the other well. Okay? What would happen if that barrier between this went up to infinity?
They're all even.
Well, they're not necessarily. They're both even and odd solutions.
The particle can tunnel in from one side, but it can't.
It can tunnel into this, but it can't get into that region, right? This region is impenetrable. It's a hard wall. It's another word for infinite barrier. It's a hard wall, right? Which means that in that case, the particle really has those nodes there. It's a little bit different when we have those nodes. So there is a solution that looks like this. And it's a perfectly good solution. It satisfies all the boundary conditions. The wave function is just localized there. There's another solution. Where the particle is localized here and then goes to 0 and then is never anywhere else. Those solutions are degenerate. They don't violate this theorem that we proved because we said something about the particle being able to extend to plus and minus infinity. When you have this case where you have an infinite barrier, you can have degeneracies. And this kind of solution, a solution which doesn't respect the symmetry of the Hamiltonian, let's just say psi is not an eigenstate of parity, even though the Hamiltonian is an invariant, is known as a spontaneously symmetry-broken state. The term spontaneous is irrelevant here. I can just call this a symmetry-broken state. That's only allowed if I have degeneracies. If I don't have degeneracies, it's impossible, because you have to have simultaneous eigenstates of the symmetry and the Hamiltonian. But when you have degeneracies, then I can take it. So what are the symmetry respecting eigenstates? Well, they're the symmetric and anisymmetric combination. So there is another solution which is perfectly degenerate, which is this one. This solution is even. It's a linear combination of the two I knew. There's another solution. That guy. He's degenerate. A degenerate solution. This is the anisymmetric combination. So, as we said, when two operators commute, there always exist common eigenstates. But if there's degeneracy, I can add these two, they have the same energy, and it would be localized on this side. Or I can subtract these two, and it would be localized on that side. So, final comment. Given this, and given this degeneracy, what can you tell me about this energy splitting between the symmetric and anisymmetric states for a finite barrier? Well, they have something to do with how much the particle can penetrate into the barrier between them. Because as I raise this barrier, this doublets will become closer and closer, eventually become degenerate. So there's something about the mixing of these two states that breaks the degeneracy. And that's an important problem that we'll study in more detail later in the notion of degenerate perturbations.